This is the first of a two-part video series about calorimetry. In our last video, we talked about heat and how it was transferred. And in this video, we're going to talk about what it's transferred to and from the system and the surroundings, about calorimetry, how we measure it, and conservation of energy, how we do calculations with it. So we talked a lot about heat transfer between objects. And so now we want to do a measurement. We want to measure how much heat is transferred, but first we need to define where it is and where it's going. So to measure how much heat is transferred, we need to define where it's going to and where it's coming from. So let's give ourselves an energy transfer situation. Let's say we have a mug of hot liquid. Could be coffee, if you're into that. All right, there's our mug of hot coffee. So the coffee liquid, we are going to define that as our system. That's the part we're going to have a laser focus on. That's the part that's going to be either giving out heat or taking in heat. And then the mug holding it and the rest of the entire universe, everything in the universe that is not that coffee, that is going to be the surroundings. And this kind of a system is called an open system because there's no lid and both matter and energy can transfer from the system to the surroundings. So when we're going to talk about heat transfer, we need to define the sign of the variable to match the convention. So when we're talking about energy going into a system, we like to use a plus sign for that. And if the variable is going out of the system, we like to use a negative sign for that. We are going to do that for heat. So heat is Q, and if Q is a positive number greater than 0, that means heat is going into the system. And if you think about the coffee being the system, if heat is going into the system, that means that the surroundings are losing heat. The temperature of the surrounding is going down. So we call this process an endothermic process. Endo means in. This heat is going into the system that we care about. And an example of an endothermic coffee system is an iced coffee. So when you put your hands on the mug of the coffee, on the surroundings, your hands are going to feel cold because the heat from your hands is going into the system. It's heating the coffee on the inside. So now for our other situation, if we have a Q value less than 0, heat is going out of the system. And that means the surroundings temperature is going to be increasing. And we call this exothermic. Or exo means out. And thermic means heat. And an example is going to be a hot coffee. This can be a little counterintuitive, so make sure you think about these examples when you think about how to define it. So if you hold the hot coffee with your hands feel warm, and your hands are part of the surroundings. So if the surroundings feel warm, the heat is going from the system out into the surroundings. So that's an exothermic reaction, an exothermic process, and your hands feel the heat. Okay. So now we know how to define the sign of the variable. So now we want to do some measurements, some calculations. So we have a formula from the last section that we can use to calculate the heat that's absorbed or released. So we can calculate it if we know the mass, the specific heat capacity, and the change in temperature. Remember that formula for specific heat that we talked about? CSP equals Q over M delta T. The other version of that formula is to rearrange it with Q as the center. Q equals M times CSP times delta T. We call this one Q equals MCAT for short. So if we know all of these variables, we can easily solve for the heat transferred. But what if we don't know all of them? Or we can't measure them all? What if we don't know all of these things about the system? So if my system is this cube, poorly drawn, oh well. If we have this cube of our system and the cube is been heated, so it's radiating heat out from the inside, maybe I don't know what it's made of. Maybe I don't know the material, so I don't know the CSP and I can't solve for the heat. What are my other options? Well, if I can't solve for the system, instead, I could solve for the surroundings. So I could build a surroundings that are an isolated system that can contain all of the energy coming out. And in calorimetry, we like to use our surroundings as an isolated container with a lid that's insulated and filled with water, so that heat transfers into the water and we can measure the temperature of the water in the flask. And we know that the amount of heat that's transferred out of the cube should be equal to the amount of heat transferred into the surroundings. And that is a feature we are going to use to solve lots of calorimetry problems in this chapter. And that concept is called the conservation of energy, also called the first law of thermodynamics. And that law says the sum of all of the energy transferred in the form of heat equals 0. So the total energy of the universe remains constant. Whenever one object loses energy, it's gained by something else. It may be in a different form, but the amount of energy is always the same. So if we define it in the same way we define these variables, we could say the Q of the system plus the Q of the surroundings will equal 0. But the system must be an isolated one. Meaning no heat or energy can escape. So that must be true for this to work. So let's define this in terms of my picture of my piece of metal. So we're going to have a Q piece for each of the different items involved in this setup. So there's going to be a Q for my hot metal. And if we know that the hot metal is the system and the heat is going out of this object, that means it's going to be a negative number. So this will be negative. And my other Q is going to be for the surroundings, which is the water. And the water is gaining energy, and if it gains energy, it is going to be a positive number. So the sum of those two pieces is going to be 0. And what we can do is that for each of these Q pieces, we can substitute in our formula for Q that we have up top, and we can use these values to solve for any values that we might be missing. So for Q metal, we can substitute MCAT, so the mass of the metal, times the CSP of the metal, times the delta T of the metal, all for that first Q piece, plus the same pieces for the water. M for the water, the specific heat capacity for the water, and the change in temperature for the water. And that equals 0. Now you might see this formula written in a different way. Sometimes you see it written like this: Q of metal equals negative Q water. And that is perfectly acceptable. That is how math works. If you move one piece to the other side, you'll get one equals the negative of the other. I like writing it in this way the best, because then I remember to add all of the pieces together and set them equal to 0. And then I'm not trying to remember which one of the pieces is going to be negative. So the conservation of energy helps us understand that all the heat transferred into one object came out of another object. And in the next video, we will use this formula to do some calculations with real numbers to understand how to solve for different variables.